Hi. So today we're going to be doing a problem in fluid dynamics. And the problem we'll be doing is, in my opinion, kind of fun because the physical phenomenon which is going to govern our problem is sort of similar to the phenomenon of an airplane flowing through the air. Now in this problem we're going to be dealing with an actual fluid, an actual liquid with some density rho. And we're going to be computing the lift on an object that is sitting inside this fluid. But in certain cases, with many approximations, the lift that we'll calculate on this object in the fluid is sort of the same as one would calculate considering an airplane wing in air, where you're treating air as a fluid. Most cases you can't treat it as an incompressible, but in some cases you can, and then it would be the same. So with that being said, what's the problem? So what we have here is an incompressible fluid. And it's flowing through a rectangular tube. The fluid has density rho. And there's some tapered object inside the tube. And what I mean by tapered is these little sides sort of go in a little bit. The object has dimensions L cross W cross H over 4, where H is the height, and you see it sort of sits halfway up. So this is H over 2 below it, H over 4 above it. We're told to neglect turbulence, so we're really simplifying the problem. And we're supposed to assume that one half of the fluid is going to flow over it. So we see this fluid on the bottom just sort of goes straight on through below. That's one half of the fluid. And then the other one half is forced to squeeze above this object. And we're supposed to compute, so compute lift on the wing. So this is our problem that we're supposed to be addressing here. And furthermore, we're told to assume that rho GH is much less than P naught, the pressure. And what that's telling us is that generally we know that from Pascal's law that the pressure below is going to be greater than the pressure above, but we're told to assume that this contribution is much less than the overall pressure, and so we're going to be able to ignore that. All right, so the basic things that we'll need to solve this problem are Bernoullis equation and the continuity equation. So let's first think about the continuity equation and how it applies to this problem. So to give us an idea, we'll draw another picture. So this is considering the continuity equation. So we have our wing here. And to understand the continuity equation, what we can do is we consider some fluid flow lines. So the fluid below, the area it has available to flow through is just a constant. So the fluid flow lines are just going to go straight on through. Nothing interesting really is going to happen. On the other hand, above, at the very top, they'll sort of go through, but then the ones below are going to be forced to squeeze over the top, and what we see here is the density of the fluid flow lines above the wing is going to be greater than below. And mathematically what that means is the velocity of the fluid is going to have to speed up above. And so if we consider the area above, so in general the continuity equation is A1V1 equals A2V2. And what that's telling us is that the cross-sectional area of the pipe here that the fluid has to flow through, if we call that A1, it's H over 2, the fluid then is going to squinch down and have less space to move through, and it's going to have to move more quickly to be able to account for that. And that's really, this is only applicable, again, if you have an incompressible fluid. If you have a compressible fluid, then maybe the density will change, and and that changes all sorts of things. But in this case, we're told it's incompressible, and so we know that the velocity of the fluid is going to squeeze up above the wing. So again, drawing a third and final picture, we have our wing here. If we consider the velocity of the fluid, let's call the velocity at the beginning V naught. We see that the area that the fluid has available to flow through on the bottom is constant, so the velocity here, again, is just going to be V naught, the same as the initial velocity. But above the wing, it goes from having sort of the width of the pipe times h over 2, and now it's squeezed to the width of the pipe times h over 4, so it has half the area, and therefore it must have double the velocity. All right, so now that we've applied the continuity equation, we could consider Bernoullis equation. So let's start by reminding ourselves what Bernoullis equation is, where it comes from, what it means. So what Bernoullis equation tells us is if we consider these three terms and sum them at any point within a fluid, an incompressible ideal fluid, then these three terms should sum to a constant. So let's look at each piece. This is the pressure at that point. Then we have rho here is the density. H is the elevation. And V is the velocity of the fluid. Again, all of these evaluated at some particular point, and then if we evaluate them at a different point, we will find that they will all sum to be the same constant within the same fluid. Now we can understand this if we think of these first two terms. This is really coming from Pascal's law. If you recall, Pascal's law is generally applied to static fluids. So you have like a fluid in a pond that's just not moving around, it's just sitting there. And what it tells us is that the pressure of the fluid increases with depth. It just, as you go deeper, it's going to linearly increase. Now the second term is the new one that we have now that we're considering a dynamic fluid, a fluid that's flowing. And this really can be thought of as coming from the continuity equation. What I mean by that is the continuity equation tells us that the fluid is moving with different velocities at different points. Now, what does that mean? That means it must be accelerating in certain places. If it's going from velocity 1 to a different velocity, velocity 2, there must be some acceleration or deceleration. Furthermore, that tells us that if it's accelerating, there must be some force, F equals ma. So pressure is just force divided by area. So what that tells us is there's going to be some pressure variation. And differing pressures at different points within the fluid are going to cause it to accelerate in certain ways. And that's going to lead to these differences in velocities. So again, this additional term in Bernoullis equation really comes from considering the continuity equation. So now that we understand the equation we want to use, let's apply it to our given system. So we could consider 3 points within our fluid and apply Bernoullis equation. Let's call this point 0, this point 1, and this point 2. So at 0, we have P naught plus rho G H naught, we could say, plus 1/2 rho v naught squared. Now I told you that we're told in the problem to assume that rho gh is much less than p naught, and so that's going to tell us that this term we can ignore. I guess it doesn't go to 0, but we can ignore it. It's negligible compared to the size of our other terms. And so in the rest of my equations, I will always just ignore this pressure variation due to height differences, because all of the other pressures are much higher. So Bernoullis equation tells us that this is going to be equivalent to the evaluation of these terms at the different points. So point 2 is easy because we get P2 plus, again, we're ignoring this term, plus 1/2 rho, just V naught squared again. So we automatically find that P naught and P2 are equal to each other. On the other hand, at point 1, we have P1 plus 1/2, again, I'm ignoring the second term, rho, and then it's 2 V naught squared, so 4 V naught squared is the velocity at point 1. So what we learn from these are that P naught is equal to P2. The additional terms on both sides are the same. And then we learn we can solve now for P1 by taking this term, moving it to the other side, and we learn that that is equal to P naught, let's get this right, minus 3/2 rho V naught squared. So now we have our two pressures and all of the other variables that we were given in the problem. So we've solved for the two pressures. But what we're asked for is the lift. So we're asked for the force on the bottom of the wing. And that directly comes from this pressure difference. So what we find is the force of lift is going to be equal to P2, force and pressure are not equal to each other. There's an area that we need. So the force of lift is going to be equal to F2 minus F1. We're expecting that there's going to be some upward force on the object. Now, of course, force is just equal to pressure times area. So this is A2 P2 minus A1 P1. Now, what is the area in question? The area, A2 is the area of the bottom of the wing, and A1 is the area of the top of the wing. Now, we weren't told the details of this tapering. We really are only given the area L times W. So what we're going to do is we're just going to assume that A2 approximately equals A1 approximately equals LW. So what we find then is this is equal to LW times P2 minus P1. And we found that P2 is equal to P naught, so we could plug that in. And P1 is equal to P naught minus 3/2 rho V naught squared. So the P naughts are going to cancel, and what we're left with is 3/2 rho V naught squared times, don't forget the LW, the area. So what we find is Bernoullis equation tells us that there's a pressure difference below as opposed to above the wing, and this pressure difference creates a force lifting the wing up, an upward force on this object inside the fluid. And again, this phenomena, this is sort of interesting to study because the phenomena can be related to considering the wing of an airplane flowing through an air and the lift on top of it. All right, so hope you enjoyed that. Thanks.